Hi everybody, another Integrity recording here, this time on solving differential equations. It's one of those awful things which you unfortunately need to know how to do for BMED 3300. So I'm going to try to take you through that. Just a little bit of nomenclature to start off with. So let me just get my pen here. All right. So here's the simplest kind of equation we're going to solve. It would be of the form dc dt equals minus k times c. And c is a function of t. That's our unknown. So in other words, we would like to know, how does c depend on time? And for that reason, we call c the dependent variable, and t is the independent variable. So when you solve a differential equation, you always try to get the dependent variable in terms of the independent variable. So if I was to write another equation, let's say df dx equals f squared, here f would be the dependent variable and x would be the independent variable. And if we could solve that, then we would get f as a function of x. Now, something I want to point out just in passing is that this is a nonlinear equation, because you can see that you have an f squared. So whenever you have the dependent variable to some power other than 1, or the dependent variable multiplied by its derivative, or some such crazy combination like that, that's a nonlinear equation. Nonlinear equations are really hard. We're not going to worry about them in this course, so don't concern yourself with those. On the other hand, this equation here is linear. C is our dependent variable. K here is a constant. So you can see we just have C, or dc dt, to the first power on the left-hand side, and c to the first power on the right-hand side. So everything's linear there, which is great. It makes things a lot easier. And just a little bit more about this equation here. This is an ordinary differential equation, or ODE. There's another type called the partial differential equation, which has partial derivatives in it. We're not going to worry about that for this course. It's too complicated. As I mentioned, this is linear, and something else you should know is that it's first order. That means that the highest derivative of c that you observe in it is just dc dt. If I had, just as an aside, if I had d2c dt squared somewhere showing up, that'd be a second order equation. But this is first order. So how do we solve this? It seems hard, right? Because to know c on this side, you have to know dc dt, but to know dc dt, you have to know c. So you're in a catch-22. You can't know the left-hand side without knowing the right, and vice versa. But that's okay. What we're going to do here is we're going to take c, and we're going to put it down over in the basement here. And we're going to take dt and put it upstairs on the right-hand side. So basically just treating the derivative like a fraction. And when we do that, we end up with dc over c is equal to minus k dt. And then what I can do is integrate both sides of that equation. And the integral of dc on c is just a natural log of c. I expect you all to know that, by the way. K is a constant, so it can come outside. And I'm just left with the integral of dt on the right-hand side, which is just t. And then remember that when I do my integration, I have a constant of integration, and I'm going to call that constant sub 1, because we're going to have a couple constants floating around. Now I'm going to take e to the left side and e to the power of the right side. And since the left and right side are equals, e raised to the left side equals e raised to the right side. So e to the log c is just c. On the right-hand side, I have e to the minus kt. And then that gets multiplied by some other constant, which I'm going to call constant sub 2. Remember that e to the a plus b is e to the a, e to the b. So that's essentially what I've written there. And so my solution is that the unknown variable c as a function of time is equal to some constant 2, e to the minus kt. And you might reasonably ask yourself, how do I get this constant here? Well, that you get from your initial conditions. So for example, I might tell you that c equals c naught at time t equals 0, and you can show pretty easily that that implies that constant 2 equals c naught, and therefore we end up with c of t is equal to c naught e to the minus kt. And whenever you have a first order equation like this, coming back up to here, whenever you have a first order equation like that, you're going to get a solution of the form c equals e to the minus kt. If this minus sign out in front here, if this was to change to a plus sign, then your solution would look like c of t equals e to the plus kt. But otherwise, that's pretty much how it works. Now, let me just show you one other small variation on that, and then we'll finish with this, which is sometimes you might have an extra term in there. So let me, sorry, I need to insert a page here. Just give me 1 second. Apologies, I should have had this ready before. So let me just give you one small variation on that theme, as I mentioned. Suppose I have the following. I'm going to have that dc dt is equal to minus k times some c minus c naught, or I think in one of the problems it was actually a c in. So why don't we do it that way. Now you can see that that's a pretty close cousin to the one that we just did, but it's not quite exactly the same. So let me show you how we get that. And here, this only works if Cn is constant. So I'm going to assume that. And here's the trick. Because Cn is a constant, I can write the following. I can say that dc dt is the same as dc minus cn dt. How do I know that? Well, what's the derivative of c minus cn? It's just dc dt minus dcn dt. But because cn is a constant, that's just 0. Right? So you can see that that's true. So using that, I can take this expression here and put it back up into that equation, which is what I'm trying to solve, and I get dc minus cn dt is equal to minus k c minus cn. And I hope you see that that looks exactly like what we had before, except instead of having c, now I have c minus cn. And so my solution is going to be c minus cn equals e some constant. Let's call it constant 3 times e to the minus kt. And again, this constant I would get from my initial conditions. So that's just a small variation. Now, last thing, that's first order equation. Sometimes you might see an equation that looks like this, say. And that idea about moving c into the basement on the left-hand side doesn't work because you cannot do this integral here. That doesn't make sense mathematically. So unfortunately, things are a little more complicated for those equations. And what you have to do is you make a guess. Well, there's different ways you can do it, but the easiest thing to do is you make a guess and you say c of t is e to some unknown coefficient r times t. You plug that back in up here. So when I differentiate e to the rt twice with respect to t, I get r squared times, or let's and let's we'll do it like this. You get r squared e to the rt on the left hand side, and on the right hand side you have k e to the rt, and you can see that your e to the rt's cancel, and that tells you that that coefficient r just has to be equal to the square root of k. And notice that there's two roots there, right? Plus or minus, because r could be the minus root of k or the plus root of k. Each of those possibilities is equally valid, so that the whole solution is some linear combination of e to the root kt multiplied by some constant, let's call it constant 1, so that's a different constant 1 than what we had before, plus e to the minus root kt, and the root sign is just on the k there. So that's our general solution, and you notice that we end up with two constants. You always have that when you have a second order equation like that. And so I need two pieces of initial data. Okay, congratulations, you're now experts on the solution of ordinary differential equations.